Okay, exponential functions. This subject is very much related to some of your science courses, like half-life, bacteria growth, and something like depreciation in economics or business studies. So the general form of an exponential function is f of x is equal to a to the x, where a is always greater than 0. Now if we look at this using autograph, okay, so what I have here is autograph. I have y is equal to a to the x, where a is equal to 1. Or any 1 to any power will be just a straight line graph. Notice it goes through this point here, 0, 1. So I have y is equal to a to the x, where a is equal to 1. Now, I can take the constant controller in autograph, and there's only one constant here, and then increase the values of a. So there's 1.2, there is 1.4, there's 1.5, 1.9 and 1.2. Okay, so let's just have a quick look at this one. When x is 1, y will be equal to 2. Okay, when x is 2, the value of y will double. From 2 it will become 4. When x is 3, it will double again and become 8. Okay, so this factor here is like the a is 2 is like the growth factor. So if I carry on increasing it, okay, the typical sort of graph is 3. Okay, so the typical sort of graph is here. Here it never really touches the axis, even though it's not. It looks like it is touching the axis. If we were to zoom in here, we'd find out that it was not touching the axis. It comes up. They all go through the point 0, 1, because anything to the power of 0 is 1. Okay, and then they increase very, very, very quickly. Okay. Now, if we go back the other way, which we can do. Okay, so we go back to straight line. We go back the other way. We get this one. Now this is an example where they're actually decreasing as x increases. Again, it goes through 0, 1. But now here a is 0.5. That's like thinking y is equal to the half of x. So it's like y is equal to 2 to the minus x. Okay, so the function here will decrease. Okay. You might also like to think for yourselves why a cannot be negative. Okay. So here are some of the main graphs here. You can see that they all go through the point 0, 1. Here I have the graph y is equal to 2 to the x. Notice it's a reflection of y is equal to half to the x. Right? As the growth factor gets bigger, the more quickly it's going to get large. This is called the exponential function. You should learn to know what the graphs look like. Here, alright, so y is equal to half is equal. It's the same as y is equal to 2 to the minus x. Right, the x-axis is an asymptote. Now what that means is that the curve gets very, very close to the axis, but never will actually touch it, even though it doesn't look like in the graph. If we were to, like I said, if we were to zoom in here, you'd realise it was not actually touching the axis. For the graphs of y is equal to a to the x, where a is greater than 0, the y-intercept is always 0, 1, because a to the 0 is equal to 1. The graph of a function lies entirely above the x-axis. The x-axis is an asymptote. I'll just explain that to you. If a is bigger than 1, then x increases. So as x increases, so does y. This is called a positive exponential. Here we have a graph of positive exponential. So this could be represent exponential growth. As if a is between 0 and 1, then as x increases, y decreases. This is called a negative exponential, and this could be used for exponential decay, something like half-life. Okay, a cannot be negative, and you might like to think about why that's so. And what we do use this for is mathematical modelling. The general form of the model is n is equal to ba to the t over k. Now each of these things means something. The initial value when t is equal to 0 will be b, because a to the 0 will give you 1, and we'll just end up with n equal to b. K is the time for n to increase by a factor of a. Okay, in a lot of cases k will just be equal to 1, therefore it won't exist in the formulae. Okay, later we'll do another example where k is equal to a quarter, because it increases every 15 minutes. If k is equal to 1, then a is the growth factor. If k is positive, then as a is greater than 1, the function models exponential growth, as I just said, and with being between 0 and a, the function will model exponential decay. Now, we have another formula where we can add c. What that does, it moves the asymptote up and down from the x-axis. Okay, so it gives you the final value. So in a later example, for example, we'll have like the ultimate temperature this thing, a body will be like something 26 degrees. So at the end here, we've got a plus 26, because that's where the asymptote needs to be. Okay, so the initial value, you need to be careful here, won't be b. The initial value in this case will be, because you're going to have a to the 0, which is 1, so you're going to have b plus c.